Hey everyone, on this lesson we are going to study and work with the distance transform. We are on the section of morphological image processing. We already did the introduction and the erosions and dilations operations, and now we are going to study the distance transform. The distance transform is basically an operation that we apply to a given image, and we have another image where the pixel value of this resulting image represents the distance from the pixel that we are measuring to the edge of the connected shape that it belongs. So let's see an example of this to make this operation easier to understand. So here we have the original image. As we see, is basically, we can see it as a circle or a cell. It is a white circle and we have a black background. And when we apply the distance transform, then we can choose the distance that we can apply. As we know, there are many distances that can be expressed in different ways, and we can choose one to apply the distance transform. Examples of some distances are, for instance, the Euclidean distance, the cosine distance, the Hamming distance, or the Manhattan distance. There are more, okay? So it is important to know that when we apply the distance transform, we can choose the distance metric that we will use. So here we have three resulting images. Here on the top on the right, we have the Euclidean metric. So we apply the Euclidean distance. And before going to explain these two below, which is basically the same operation but with another metric, let's take a look at this image, or at any distance transform image that we get. Here it is very important to know that the main point on this shape, that is the point on the middle, okay, on the center, basically the pixel that we have on the center of this circumference, is basically the color white. So it is 1, right? Why? Well, because this is the point where the distance between this pixel and the edge of this shape, of this circle, is the maximum, okay? As we move away from the center, then we get closer to the edge, and then this distance, which is the distance from the pixel to the edge, is decreased. So it is important to know that always the center of the shape is the one that is more white, and as we move away from the center of the shape, then we get less white. So as we see here, basically the edges, all the pixels that are very close to the edge, are some sort of blackish. Okay, it is basically almost black. Why? Well, because now the distance, as we move closer to the edge, is closer to 0, until the distance is 0, when we are on the pixel in the edge. So basically, all the pixels of this circumference of the edge, the contour, is basically 0 on this resulting image. And this is important for any given distance transform that you perform. You will have this, and regardless of the metric that you choose. Here, for instance, we apply the C8 metric distance, and then we apply here the C4 metric distance, but the idea is the same. We compute the distance, and the less distance that we have on the pixel that we are dealing with and the edge, then the more black the pixel will be, and the greater, or basically the larger the distance of the pixel from the pixel to the edge, then the more white the pixel will be. Okay, so we have here these two partial results. So since we are always representing the distance from the pixel that we are computing to the edge of this shape, the surface of the values of the pixels have this shape. As we see, the pixel that is on the center is the one that has more value. It is more white, because as we know, if we have gray levels, then 0 is black and 1 is white, right? So here it is basically the maximum value. And as we move closer to the edge, the distance is less, so then the pixel also has less value. Very well, so with this we have all the information that we need to start working with the distance transform. So let's introduce this operation of distance transform from the information that we already know, for instance with erosions. So to work with this, we have this image, which is the image cells. You have this image available for downloading in the downloadable documents of this lesson. So let's read this image with the imread, and then we just write here cells.tif, right? So then let's display this image. And let's title this image to be the original image that we have. And we run. So as we see, we have here the original image, which is basically two cells. We can see that they are two cells that they are touching. Okay, each one is touching each other, as we see. Now, to apply the distance transform, we need to first remember how to erode the images. So remember, to erode an image, we need a structuring element and the original image. So in this case, let's define the structural element, SE, to be the structuring element with this function. Remember that this function allows us to create structuring elements. So the shape is going to be a disk and the radius is going to be 1. And this is something that we explained on previous lessons. Then we can erode this image and apply the erosion operation. Let's define the resulting image ero, and we can perform a erosion operation with the im_erode function. Okay, this is a function that receives two arguments. The first one is the original image, in which our case is this one, and then we have on the second argument the structuring element, which is this one, right? So now in a new figure we are going to display this new image, which is the eroded one. Everything in here are concepts that we already know how to do, and then we are going to title this the eroded image, and we are going to run. And here we have the eroded image. Keep in mind that the difference is not too big because we only have eroded 1 pixel. The radius is 1, right? As we increase the radius, for instance 6, okay, then the visualization is more powerful since the erosion is stronger. So for this example, we will use and remain to the radius 1. Okay, but remember that when we apply erosion, we are making basically the shape look thinner. So we are some sort of shrinking all the pixels that we have on the shape, right? So we will leave from now the 1 radius. And remember also that we explained how to calculate the residue with the eroded image and the original image. Then we can define the residue to be basically the shore between the original image and the eroded image, right? So in a new figure we can see this with the imshow we can see this new image, which is the residue, and let's title this for instance the residue image. We press run, and as we see we have now the residue image, which is the gradient of the image and also the contour of this shape. Now let's apply now the distance transform. And to apply it, what we will need to do is to sum the original image with the eroded image many times. So first of all, let's define this t_dist image, which is going to be basically the original image, but we need to convert the original image from Boolean to double. That's because we are going to sum images, and if we have a Boolean image, we cannot sum it. So first of all, we sum the t_dist with the eroded image, like so. Here it is the first sum. And then what we need to do is to erode again. So we take the eroded image and we apply the im_erode function to the eroded image with the structuring element that we had before. So as you can see here, we are now updating the value of the eroded image, and we are going to erode the eroded image. So instead of eroding, okay, this original image, we are now eroding the eroded image already. So it is 2 times the erosion that we had before. And after eroding again this image, we again sum the t-dist plus the t-dist that we have plus the eroded image, like so. So we're going to do this many times, and this is the way that we apply this distance transform, and the way that we get this distance transform resulting image. So let's do this many ways. The easiest way is copying this and do it many times. So let's do it many times, like so. We have this first line, then we have the second line. Keep in mind that what we're doing is many times eroding the previous eroded image. So at each iteration, we are eroding more the image, and then we are summing the distance plus the eroded image that we have on that moment. So let's do this again and again, for instance, 6 times, 4, 5, 6. So that at the end, at the image t-dist, we have the distance transform. And now keep in mind that from this original image that we see, pixels that were at distance 1 have the value 1, pixels that were distance 2 have the value 2, and so on. So let's comment this and note it in here. Okay, let's put it in here. And let's display this final image in a new figure. Let's show the image distance transform, which is t-dist, in gray levels. We're going to specify the minimum and the maximum range, because this is no longer a Boolean image, but it is a double image, right? And let's title this in here the initial, let's call it initial distance transform, right? So also more important things, well, this image represents the information, how distant you are from the border of the shape. So let's also comment this, because it is important. And finally, let's run this and see this final image. So as we can see, we have this distance transform image, right? So let's verify that we have this shape-like view, in the sense of on the center, the pixels on the center are the ones that have more value because their distance is greater from the edge. And as we go and as we move closer to the edge, then the distance decrease. So the value for the pixels also decrease. So to see the shape, we can apply the mesh function. Remember that the mesh function in a new figure we can display. This is a function that it creates a mesh plot, which is a 3-dimensional surface with solid edge colors. So in here we just pass the image, which is the distance transform image, and then we title this to be the mesh, okay, or the surface of distance transform, like so. So let's run this and verify that this is indeed working and it satisfies the condition of the distance transform. So as we see, we have this resulting mesh plot, which is basically that represents that this is working right. As we can see, the pixels that are on the center of the figure are the ones that have more value, and then as we get closer to the edge of the shape, in this case we only increase the shape by 1. Why? Well, because the radius, remember, the radius of the structuring element of the erosion was 1, okay? So as we get closer to the edge, the values for the pixels decay and decrease. We can make this decreasing faster by increasing the radius of this structuring element. For instance, let's use 3 and let's run again. So now we have this eroded image, we have the residue image, and we have the same distance transform, but now as we get closer to the edge, okay, we are decreasing the values of the pixels by 3 at each time that we sum and we perform this sum of the transform that we are applying. So also the disk shape is not the only one that exists. We also saw the rectangle shape or the line shape. There are many shapes that we can use. since this original image has a circular shape and some sort of circumference, that's why we're using the disk, but you can use any structuring element that you want. Keep in mind that this structuring element works as a kernel, if you remember the linear filtering, and you can your own define a matrix for your own. So you can define a matrix that is nothing more the structuring element. Okay, so you have many possibilities in here. We will study all of them in the future. Okay, this is only an introduction lesson to the distance transform. Now we have reached a decisive point right now. Why? Well, because why have we named the image to be initial distance transform and not distance transform? Well, the reason of this, let's remain again the value 1 for notation, but you can use any radius as you wish. Okay, let's keep with the same radius that we were using before. So we have named this to be initial distance transform because we can keep applying these operations over and over until we erode completely the image. So at the end, we will have a full eroded image. Okay, so we will only have the background. All the shape is going to be fully eroded. And this is the distance transform. This is how the distance transform is applied. You have to erode the whole shape. So now let's define a very, very simple algorithm. So basically we will verify and we will apply a while loop, and we will use the function any on the image ero, which is the eroded image, like so. So what we're doing now, we're basically checking if there is any non-zero element inside this image. The any function, if you have any in the image, for instance, or give an array, because an image is nothing more than an array, then you use, for instance, all the elements of the array, you check if there is at least one non-zero element. So we are basically doing a loop that while there is at least one non-zero element, okay, of the eroded image, it means that we haven't eroded completely the image yet, so we will keep doing. So while there is at least one element that is not zero on the array, then what we will do, well, the same thing, we will erode the image with the imerode function, imerode, with the structuring element that we have chose, and also we will increase the distance transform, okay, by this erosion. So here we just increase, like so. And then we will end, we are going to end in here. So basically what we are doing is we are going to check if we are done with the erosion, and once we are done, once we have eroded completely the original image, then we are going to apply the distance transform. So basically the distance transform is going to be already done after the ending of this loop. So let's now in a new figure verify that the erosion is completely. So let's apply the imShow function to show the eroded image, and let's title this verifying if erosion is complete. Okay, so now let's plot this, let's run, and as we see we get this resulting image. So this basically means that the erosion is done. From the original image that we had, we have eroded completely the image, so the shape of that we had is thinner, and thinner, and we have shrinked the image completely. So this means that the erosion is done. So now let's figure and plot the distance transform. So in this case it is the image dist, and this is the distance transform that we wanted at first. Okay, so this is the formalization of the distance transform. We keep eroding any given image with the given structuring element that you choose, and you keep increasing the value, okay, depending of the erosion that you have. So let's run this, and before running, remember to add this, because this is a double image, it is not a Boolean image, so we need to add the minimum and the maximum to be inferred by the MATLAB system. So now we run, and as we can see, here is the solution of the distance transform that we wanted, okay, at the beginning. So as we can see, this is the distance transform, where the values at the center of the shape have more value, and as we move closer to the edge, then the value gets decreased, right? So let's now verify with the mesh function that this is indeed a correct distance transform. So now in a new figure, we are going to apply the mesh function, okay, of the distance transform image, and let's title this the surface, okay, solution surface. So we run. So as we can see, we have here the final result and the solution that we wanted. Okay, the points and the pixels that are on the middle of the shape, they are the ones that have greater value. And as we move closer to the edge, then this distance is less and less and less until it reaches 0. And as we can see, it has the same shape as we saw at the example. So with this, we end the distance transform lesson. We remind the student that you can download all the code that we have written on the downloadable documents of this lesson, as well as the image that we have used and the slides shown at this lesson. See you at the next lesson.